What I want to look at today are two problems, but really the same problem, and dealing with a problem where you have a combined rolling with and without slip. And threading the spool refers to a typical problem that we often have in the course, which is you have a spool which is on a ramp or on a flat surface. And what we want to do is look at this from two different chord locations. So I'm going to adjust the chord length or location and sort of discuss a little bit about how and why this affects things. So main condition for rolling without slip is that the friction force not exceed the maximum possible for a coefficient of static friction mu sub s. So that you already know what that is. This down here is bad latex, and that should be 27 degrees. So I have a cord that's wrapped around the inner hub of a wheel and pulled with a force of T. The wheel has a mass of 350 kilograms, a radius of gyration of 1.7. So 2 meters and 1.5 meters for the inner radius, 2 meters for the outer radius. Knowing that the static friction is 0.33 and kinetic friction is 0.29, determine the acceleration of that center of mass G, the angular acceleration of the wheel, and the tension T in the cable when the spool is released for rest. And I have two cases I want to look at today. One, the cord is attached at the bottom, so you see it right here. And the second one is the cord is attached at the top, so I've just shifted it. So it's kind of hard to see how this would affect things, but let's continue through the problem. And maybe at this point you've already looked at a couple of these. So if I draw my free body diagram, I'm going to have weight, which I've sort of not reoriented, but it's down and downward here. I have tension on the bottom, and I have normal force, and I have friction force. So let's talk a little bit about the friction force. Since that spool rolls without slipping over the rope, the spool must slip on the incline if it's to move, because otherwise it can't roll without slip at both locations. A counterclockwise rotation of the spool will cause the friction force to point down the ramp. So there you go. It's rotating in that way. And so the friction force is like this. So the problem with these examples is that it requires a little bit of intuition and a little bit of drawing of these things to see it. So if I look at the sum of forces in X, I have force friction, which is acting down the ramp, which is my positive direction. I have tension force, which is acting in the opposite sense, which is negative. And I have weight, which is acting downwards. And this is theta. So it's positive because it's acting in this direction. And that is mass of the spool, acceleration of the center of mass in the X direction. Next thing is the normal force, which is acting upwards. I have the weight component, which is acting downwards, and that's mg cos theta. And finally, I have force of friction from the outer spool, so it's causing a rotation in the clockwise direction. I have temperature or tension in the cable, R inner, and I have Ig alpha spool. So Ig is mkg squared because I have the radius of gyration. Force of friction, I know at the spool surface it's going to be mu sub k because it's not rolling without slip. And I can sort of say agx for this is going to be a minus r inner times alpha spool. I can do this using vector approaches, and if I do, I don't have to sort of assume these directions. I'd have them already in there, but this is how I'm going to sort of go at it. Acceleration g in the y direction is 0 because this spool doesn't bounce. So if I substitute back in all the terms, some forces in x, some forces in y, some moments about g, I end up with alpha of the spool, which is mu k r outer minus r inner cos theta, r inner sine theta, r inner squared kg squared. Normal force is mg cos theta. And I can also do the same thing for the tension, just substitute in terms. Mu k kg squared r inner r outer cos theta plus kg squared sine theta r inner squared plus kg squared. So now if I look at the second case, In the second case, I have the only difference is that the force of friction is going to be acting up the ramp, and I have tension in this direction, which is sort of going to cause motion in this direction. Again, same reason, center of spool, point of contact, all of that, and the friction force is up the incline as shown in the free body diagram. Again, I have the same angle, so theta over here, but I'm going to start changing some of the terms. And so those terms that are going to change are going to be force of friction, force of friction here. I have this term which goes differently, and I have force of friction is mu kn still. I have all of the same terms here, so really the only thing that's changed is these two terms right here. So if I go look at the forces, I have all of these terms again. So I have mu kn, force of friction, minus T plus mg sine theta equals mass times r inner alpha spool. That's my AGX. I have AGY, which is equal to 0. And I have some moments about the center, and it's only going to be the frictional force, the moment caused by the frictional force, and the moment caused by the tension. That's going to be IG mkg squared times alpha spool. And so the equations look a little bit different. These signs change, and these signs change. So out of this, for the two solutions, I get, first of all, for the lowercase t equals 1893 newtons, alpha of the spool is minus 1.05 rads per second, and acceleration is 1.58 meters per second squared. If I go on the other side, so if I just change the location, it's 895 newtons, still an alpha of the spool of minus 0.43 rads per second, and now a spool of the x, which is 0.639 meters per second squared. So why do I want to do this example, and why do I think it's important for you to look at it? This is a hard to visualize problem, and it often proves challenging to students, and frankly to me when I first saw these things. And it's good to sort of go through problems like this and really think about friction. And when you do that, you'll start to appreciate some of the challenges of these problems, but also think about how you're going to solve them in the future. So thank you very much, and we'll talk again in the future.